Yes.
All right, thank you. Thank you. Okay, so what we're gonna do today is to do some more problems using the Smith chart, and I will develop a problem similar to your homework so you can see how I'm gonna do this. And I will do it on Smith chart because your homework, the individual homework, is kind of easy otherwise, but I will do something similar so you can see how I would approach it. All right, let me, in fact, any questions, however, before I start? Any questions? Okay, I hear none. So um, I will write the problem here, and I suggest every time, whenever I give you a problem to solve, draw the problem the way I give it to you, and then write the what I'm giving you, so the given parameters, and then write also what I'm asking you to find. And when you do it in that way, then you're not going to forget. A lot of times when you use my figures to solve a problem, you don't necessarily get engaged with the description of the problem. It's a different way. Your brain is going to learn in a different way if you try to draw it yourself. Then when you put the parameters, you know what it is in front of you, because a lot of times if you don't do that, then many of you it's easy as a human being to forget something. And then when you forget one of the parameters, then when I'm asking you to find something and you don't have it available, that may really either make it impossible for you to solve the problem or lead you into a totally different for the solution. So that's what at least I always do. So the problem here, so I'm going to ask you, I will rather give you a transmission line. The transmission line here is going to be similar to the one you have in the homework, but not the same. So it's a line, I always do this. I always put thick lines for the transmission line. I never use the same because then it can be very confusing. And then this line, in fact, is going to be, so I will do it a little more difficult than your homework. So I will assume that this line has two sections. And so the other section is gonna be here. It's gonna be here. And then in between these two, and then I will use a thin line to show the in between. Oops, not that one, this one. I will use, yep, this line. These thin lines are like the ones we use in circuits, all right? They don't have physical length involved. That's why we always try to make sure that the transmission lines are thicker, so visually we can differentiate them. Transmission lines have lengths, thin lines don't. We just show connections, all right? And so practically what I will show you is here at this point is gonna connect to another transmission line, all right? And this other transmission, let me see, line, look carefully, is going to be, let me use a different color, like this one. And it's gonna be thicker. And I will do it like this. All right? And at the end, this other line is gonna have also an impedance. So like in your homework. So, and then the lines I'm gonna use are thin here. So here you're gonna have an impedance here. all right? And this is Z, say 2, and you have an impedance at the other end, Z1, all right, Z1. And then you have the following that I'm giving you, that these are have Z naught, characteristic impedance Z naught, that this length here is D naught, this length here, let me see, is D naught. I could give you a different one. I'll give you D naught. And then this length here is D1, D2, say. In fact, I could make them D2, like this, there, there. So I can call this one to be D2. And then in fact, I can call this D1, just, and then I can give it, I can give the symbol D1, just for that. And now I will put here, at this point is A prime, B prime, C prime, and D prime. All right? So this is my transmission line. And in this one, I can move it a little further down so I can put the data on top because I will need more space in this. So what I'm giving you is the following. I give you that Z, first of all, Z naught is 50 ohms. I give you that Z1 is, let's say, 100 ohms. I give you that Z2 is 50 minus J 100 ohms. Okay? And then I want you, yes? Is Z equals 50 in the kind of standard yeah, Z naught is always, in the largest percentage of interconnects, you have 50 ohms. It's almost like a standard, but it does not, is not in all of them, all right? So you may have, at least in intermediately, you may have to put a different characteristic impedance in some sections of lines when you design functionalities. But yes, it's almost like a standard to be 50 ohms. But you expect people to tell you, and if you don't see it, you will assume 50, but make sure that that's correct. Okay, you're welcome. And then what we have, what I'm giving you is D0 to be, say, 0.1 lambda. I'm giving you D1 to be 0.2 lambda, and I'm giving you D2 to be 0.25 lambda, or 1.5. Just let's do that, 1.5. Okay, just whatever. All right, so now I have given you everything that you need to know at this point. And I may also give you a source up here. Oops, sorry. I may give you a source on the left side. And this source may have an internal impedance ZS. And then V naught, I can make it equal to 1 volt, and ZS. And I could give you, as I said here, V naught is 1 volt, And then I can give you, make it a little darker so you can see it, that ZS is say 80 volt, 80 ohms, right? Excuse me. All right. And I may ask you to do two things. So then I say find, first of all, the Z input at A prime, number one. And then number two, find the current that flows like here through this port. And then find A prime. Okay? Now, and I ask you, find all of this using the Smith chart. So using the Smith chart. All right. Now, how I'm going to think about this problem? There are some things now that so practically that's what you have to do. From problem one down, you will have to rewrite those things. So you have all of your data up there. You have what you have to find down here, and you have developed the whole, when you rewrite, when you sketch out your problem, then you realize what you have in place. There are so many times when students have said, who are trying to learn, oh, I did not see that. I did not see this thing there somehow. But if you do it yourself, you're going to see it, all right? That's why you have to write it before, even if you spend like 5 minutes doing that, it's worth time spent. All right, so now in the solution, you have to be also in the solution, be systematic on how you develop it. When you are systematic and have an approach, then you will not get confused. And you're also with an approach, you're not going to get confused within your own writing. Sometimes I have seen that, especially in midterms, the students write everywhere and they don't know what to get after that. I mean, you are, of course, under stress. And because it's not clean, it's easy to make mistakes. So here I'm outlining the solution outline, before I do anything. Outline. What I need to know, for example, is I need to, what I need to remember rather, number one, normalize, to use the Smith chart, we have to normalize impedances, all right, all Z's, and normalize all lengths. However, and all lengths. However, the way I have given you the lengths here, they are not physical lengths. See how I'm giving you the lengths? The lengths that I gave you are in the form of a wavelength. So they are already normalized with respect to the wavelength. And what we said is that the Smith chart does not take physical lengths. It takes electric lengths. What is an electric length? It's a length normalized with respect to the wavelength. All right, so it takes only that. And what else does it take? Normalized impedances. With respect to what? To the characteristic impedance. Okay, so now I'm gonna do that. I'm gonna normalize the impedances. First of all, I would normalize Z1, and I gave Z1 to be 100, so Z1 is 2. Okay, then I'm gonna normalize Z2, and I gave you Z2 to be 50 minus J 100, so it's gonna be 1 minus J2. All right, these are important. Now I can go on the Smith chart, but I'm not gonna do it until I decide how I'm gonna solve the problem. All right, it's like building a house. You develop the plans on how to do it, and then you start building it. The same thing with the solution. Don't start the solution. Listen to me. Don't start the solution of a problem if you don't know how to get to the end of it. Don't start thinking, I'm going to explore this forest. You don't solve a problem like this. All right, you have to outline your solution and then take the steps. Because a lot of times you start doing things, when you start doing stuff without knowing how to get to the end, you do all kinds of crazy stuff, and you spend so much time doing things that don't have relevance. So outline the solution. I'm gonna do 1, 2, 3, all right? So here I'm gonna do that, outline. So I'm gonna do it as part 2. To be able, so let's look at that. To be able, what do I have to do to be able to find the input? First of all, the way it is, there is no way I can find it. First of all, number one, I'm using the Smith chart. I'm not expected to write equations. It's not gonna be right, okay? Equations will not have, and if I write, it has to be a small one, not something from the beginning. So I'm not gonna do anything with equations here. So what am I gonna do? First of all, I will have to transfer this Z1 to BB prime, all right? So I'm sitting now at BB prime and I'm looking towards Z1. So what I'm gonna do is that come here and find, and I'm gonna do it with red, I would like to find this input impedance, which is Z input 1 at B prime. And that's the input impedance that I see while I'm sitting at B prime, looking towards Z1, okay? So that is number one I have to do. Then what is number two? I'm sitting at BB prime, I'm gonna try to find the impedance I'm seeing this way. And that is the Z in 2 at BB prime. So it's the impedance, I make the lines, the arrows a little longer so you see which direction I'm seeing, all right? So the green one is I'm looking towards Z2. So I have to find that one. Now, what do I know? The moment I found this, okay, so I find here, I outline, as I said, my solution. So I have to find, first of all, find Z input 1 at BB prime, and then Z input 2 at BB prime. And then what am I gonna do? Since I'm sitting on BB prime, I will replace the lines with their equivalent impedances. So here, see how it's gonna look. So I'm gonna take now this part. I'm not gonna draw the whole thing. I'm gonna only take a part of it. Copy, and then I'm gonna go here, paste, okay. And whatever I don't, since I'm gonna replace the lines, I don't need this one. All right, I don't need this one. Since I found the impedances, their equivalent impedances as they transfer to BB prime, what I'm going to do is the following. I may write it because it was. So I am at BB prime, B prime, and then, excuse me, BB prime. And then what do? I place there the impedances that I see. So what is characteristic? That these two sections of lines, one which has the distance D1, the other has the distance D2, they are sharing the same voltage. So they are connected how? In series or in parallel?
Parallel.
In parallel, absolutely. So then I place now the two impedances here. One is this impedance, and I'm gonna change their color so we don't get confused. Make that, and the other is this impedance, and I make it green. Okay. So then I will place the two impedances here. One is that, and that's the Z in 1 BB prime. And then I will make this one red, red. And the other is this one. Also, what did I say? The thin lines that I have there have no length. I only use the thin lines like we use them in circuits. When you put a capacitor, when you put a resistor like this, and a capacitor next to it, and then an inductor, is there a distance from here to there, physically speaking? No, in circuits. There's no distance. You just lay out your circuitry like that, and you do it on paper, so obviously you introduce a physical dimension which does not exist there electrically speaking. All right, even if electrically speaking, when we operate these circuits, we operate them in DC. And when you have DC, it's like for the current, it's like everything is there. We just place it though, physically, all right? But electrically, there is no distance between here and here. Electrically, there is no distance between here and here. There is no physical distance between there and there. The only thing that you have is a resistor, is a capacitor and an inductor, and obviously electrically, they change the circuit, all right? Their presence is visible electrically speaking, but not physically, all right? So now all of these lines, I'm telling you that, and I will keep telling you this. So all of these lines that I have here do not mean anything. They're all right at BB prime, okay? So now that is my step 2. After I have done this, and obviously all of this will be normalized, all right? You remember I'm working on the Smith chart. So obviously whatever I see on the Smith chart they're gonna be normalized. Okay, so now that I have those in parallel and I know them, what am I gonna do? What do you do when you have two impedances in parallel and you know both of them? How do you find the equivalent impedance? Yeah, we're using the parallel combination of two impedances. Okay, so practically here, I'm going to replace it with the total impedance, which I call it Z sub T. And this is going to be the parallel combination of these. And this means one rather. Parallel with this one. That I can do, in fact, even if I will show you how to avoid doing any equations. But at this point, we will only do this parallel combination. And then we are going to replace these two parallel impedances with Z sub T. So the next step is going to be as number, so this was number 2. And then number 3 will be to take this circuit, copy it, come here, place it, okay? And then what I'm going to do is remove this and place only one impedance at the end, which is going to be Z sub T, normalized. And then I have now only one section of a line with a load at the end, and then I will go on the Smith chart to find the input impedance. All right, so here. Oops. So I need to find on the Smith chart using that. That's how I'm gonna outline my solution. And I'm gonna do it without doing those things. I'm telling you, you're not gonna fare well in trying to find a solution to a problem. At least in the beginning. When you get more experience, you will not have to do that. But for now, all right. Then let's try to do it one at a time. But we are gonna do all of this on the Smith chart. Okay, so let's use this one. And here, first of all, you remember what we have to find? We have to find Z input for 1 and Z input at BB prime for 2. Let's start with Z input for the one case where Z1 is 2. So let us try to find the location of Z1 normalized on the Smith chart. Z1 normalized on the Smith, and then probably, um, let me copy that. No, I will copy, I will do it here. So don't throw it away. All right, let's try to find how we are gonna find this Z1 normalized is 2. So where is it on the Smith chart? It only has a real part. So where is it gonna be? It's gonna be the real part shows along the horizontal line. And I'm gonna look at 2, which is here. So we have that, now I can see 2. And that is the point Z1. Okay, it has only a real part. Then I wanna move this, all right, you see what I said I will do? On from here, I'm gonna go and find the input impedance of this section of the line where it has a load of Z1. And that's what we did last time. So I'm gonna go to move along the line, this line that I'm outlining here, I have to move on its circle. Remember we said every line has its own circle. Okay, we need to go and find this circle. How are we gonna find this circle? This circle here, the circle of the line, it has to go through, it has to have a center at the center of the Smith chart and go through this point, all right? Because this point belongs to, this is the load of the transmission line. And this, the circle for this transmission line has to include that point. So I'm going to use a different color, obviously. Let me use this one. So we don't, because we need these colors. And I will develop this circle. Hopefully it's not gonna be a correct one, but I will fix it. And this one is gonna be there. I think I'm right somehow. It is not, I'm not sure, it's a little bit confusing, something like that. Okay. This look like a nice circle. I don't know what it is, but it does matter. Okay, that's my circle. And then what way would I have to do to be able to find Z input for this line at BB prime? I will have to move on this line. And I will have to move from the end of the line towards the source, the generator, all right? So practically.
I had a question.
Yes.
You may have said this, but how do you know how big to make the circle?
Okay, so the circle has its center at the center of the Smith chart.
Yeah.
And goes through the point, which is the load.
Yeah.
That's how
Okay.
I find it. Okay.
Okay.
There's only one circle. All right. So now then we do the following. We have to find out which direction we're going to move. To see what direction you're going to move, first of all, remember that that shows the direction we are going to take when we move towards the generator. Let's see whether we are going to move towards the generator. Now, to be able to find Z input, I have to move like this. You agree? So I'm moving towards the generator. That's where all of my power comes from the left. So then I will have to move from Z1 like this direction, like clockwise, and I have to move in this line. By how much? How much I'm gonna move depends on how the distance is. Distance D1 is 0.2 lambda. This is the distance for this part of the line, 0.2 lambda. How am I gonna find this distance? First of all, I need, if you remember, to write a line that connects the center of this circle, which is the circle of this transmission line section. I have to develop a line that is, and I will do this line, say with red, and this line is going to be from, not this, sorry, this one, red, and it's going to be from the center, going like this. But also what I will do for this line, for this particular case happens to be there, I will change the style and I will make it like that so you don't get confused, all right? So this line is this dotted line, and what we find is where exactly we have to move at the outer rim. We are moving towards the generator. So I will have to go on here, and then I will have to see what number this line is showing, which is 0.25, all right? In this particular case, the number here, and I will also do it like that, this number here is 0.25, and it's in lambda, 0.25 lambda. Then I need to move towards my generator, which means like that, and I will need to move by another 0.2 lambda. That's what I said the length of the line was, did I? I said the length of the line, of that section of the line is 0.2 lambda, so I have to move by 0.2 lambda. If I am at 0.25 and I move by 0.2, it's like I'm adding 0.2 to that, all right? So practically, I will have to move by 0.2, so I have to reach this point, which is given by that. I have to find the point, 0.45 lambda. That's where I will stop. Where is that point? How am I gonna find it out? I'm gonna go on the same outer ring, and I'm gonna be looking from 0.45. And this point is here. See, 0.45. So then I will connect this point with the center of the Smith chart, and I will do another green line, because red I start, green I stop, and then I will do it like that for now. It's gonna go here. And also I'm gonna make it like this. And then I see where this line intersects the transmission line circle, which is right here. All right, right at that point. Right here. So what I'm gonna do, I have to move from Z1, where you see it normalized, to this point. And usually, and I suggest you do the same, I do these arrows to know how I'm moving, because otherwise you may make a mistake if you forget which direction you have to move. So do that. Put these arrows so they remind you that you are moving on this line and you are moving along this direction. For me, I always do that. It's a little bit of work, but it's visually very easy to see what you've done. Now you're moving along the line, all right? So you see the motion. So then, what is this point here that I'm arriving to? That point is Z input. I'm gonna write it here. This is your impact, and I had it with red all along. So this is your Z in 1 at BB prime. This one, this point. All right, so that is your Z input normalized BB prime. And let's read to see what this is. To read it, I'm gonna impact, and then here what I will do something more. I will take this, move it here, okay? Because it's clean, you can see it. And then what I will do, so for you to see, I will go from here and say, this is my point. All right, and now let's try to read it, how much this is. How are we gonna read this? We have to find its real part. How do we find the real part? I'm not gonna draw circles. I'm gonna just show you how I'm gonna do it. To find the real part, I'm gonna go like this. All right? Until I'm going on this circle, it's the constant resistance circle that goes from this point, and I see where it intersects the horizontal line, and it is point, you see 0.5, 0.6, 0.5 is to the left, 0.6 is to the right, is a logarithmic scale. So it's gonna be 0.55, and probably that's gonna be 0.57. So it has a real part, which is I need to change that, is, that's correct, 0.57, and then has an imaginary part. How do I find the imaginary part for this? I will also show it like that. I'm gonna go along this axis. This is the circle that goes through this point, and then it gives me the imaginary part, which is gonna be down here. So the imaginary part is gonna be somewhere here. I have all of this here. This one, that's why it is there. If you go, and if you have to read it on the inner circle, you have to read that here. And when you read it, it's gonna be 0.2 just above it, 0.3 below it, and it's then 0.2 is in between 0.2 and 0.22. So I will write, and it's 0.21. It's approximate, but it's good approximation because of the second decimal. And it's below this, the center, below the horizontal line, so it's negative. All right, so this is gonna be 0.21. So now I found that impedance, okay? I'm gonna do exactly the same thing, and I will do it on the same Smith chart. I will do now exactly the same thing with the other line that goes like diagonally, all right? So I'm gonna try to do exactly the same with this line. And to find out how much is the green impedance, Z input, Z2 input at BB prime. All right, I will do exactly the same thing. First of all, I need to find Z2 normalized. Z2 normalized is 1 minus 2J. So to find that, I'm gonna do it here. You can do it someplace else, but let's do it here. Do you want me to do it on a different, or you wanna do it here? You can do it here because you see what you've done before is going to help you, right? So Z2, what did I say? It's 1 minus J2. 1 is the circle that gives the real part of 1 is this one. That gives real part of 1. So my point is somewhere there on this circle. And then it's minus J1. The reactive part that gives minus J is this one. All right. So my point practically is, I will put it green. My point is this one. It has a real part of 1. It has a negative part of minus. Did I say J1 or J2? It's 2J, right? 2. Okay, so it's not even there. It's a little further out. Still on the same circle, but it's going to be where there is 2. So it's going to be this one. I thought it was 1 for a moment. Here. It's going to be on this that goes through 2. So practically this point is not there, but it's down here. Here. That is my Z2 normalized. All right, is 1 minus J2. Okay, now again, I'm gonna write the circle of this section, transmission line, because these two transmission lines have different circles, all right? They're not the same. So the circle for the green point, which is like the transmission line that goes diagonally, is going to also have its center at the center of the Smith chart, and it's going to go through point Z2. So now I'm going to write a different circle, bigger one. Okay, I'll fix it. So it goes a little further, goes like this, a little further, goes like this, further. Yeah, okay, more or less that. That is the green circle that goes, that is the circle of the transmission line that is going diagonally. Now I will have to do the same thing. Again, on this line from Z2, which is down here, I have to move in that way. So I'm moving from the load towards the generator. The generator is always, all right, to the left of the load. So I will have to move towards the generator to get to the point BB prime, where I will find the impedance. So I will move again in the same way as I did before. I will move along this direction. And so from Z2, where I am, I will have to move by 0.15 of lambda. So first of all, I need to find where I am. So the same way as I did before, I will write a straight line that connects this point Z2 with the center of the Smith chart. There, I will make this line to be dotted. And then I'm gonna go here on the outer rim and see where I am. And I'm right here. And I will read this number. So this number that I will read here is going to be what? It's going to be 0.31, 0.312, 0.31, 0.312, and it's 0.313. So it's practically 0.313 lambda. Now, that's where I am. I have to add to this 0.15, because that's the length of the line, all right, that I have to move. So I have to add to this 0.15 lambda, which makes it equal to 364 lambda. So from where I am, from this point, which is at 0.313, I have to move to this point. Okay. Has problem there. All right, I have to move from this point, which is 313. I have to move to this point. And where is that point? I have to find it here. It's 0.463 lambda. This is 0.45, we were before. 0.46 is right here. And I have to find 0.463. So, which is here, 0.463, that. So I have to stop there, but how am I gonna know where to stop on the green circle? I will have to connect now, let me use a different color. So there are too many greens there. This line, this center with this point, also make that dotted. And I will have to see where that intersects with my circle for here. That point, as a matter of fact, is going to be this other input impedance, and is going to be Z in 2, normalized obviously, at BB prime, and I will have to read it. So it's gonna be here. How much? I have to read, the real part is from here, which is 0.1, is 0.1 and this, 0.1, 1, 2, 3, 4, 5, 6, 7, say 0.17, 0.17, and then it's negative, is below the line of, on the horizontal line on the Smith chart, so it's gonna be negative. And how am I gonna read the reactance? For the reactance, I have to follow the circle of the reactances. So practically it's gonna be along that, all right? And if I see where that goes, I will find that it's somewhere here. And if I read that, it has 0.2 above it, 0.3 below, but it's 0.2, 2.2, say 3. So that is gonna be minus J 0.23. All right, so now I found, using this approach, the two impedances. I'm going here to write them down. So what I have found from here are from the Smith chart are the two impedances. So I found that Z input at B prime 1 is, according to this, 0.57 minus J 0.21. So it's 0.57 minus J 0.21. And Z2 BB prime will be how much? Here, 0.17 minus J 0.23. So it's gonna be 0.17 minus J 0.23. And practically, I have to highlight those so I remember them. All right. Now, you have a calculator, and assuming I don't. So what would I do? How would I go and combine in parallel two impedances that do not have, if I don't have a calculator? Nothing. And I don't have even paper to write down. Only have the Smith chart. I don't have paper, I don't have pencil, but I have whatever I need to do here for the Smith chart. That's a question, all right? That is important, and keep it in mind. So let me tell you another thing which we have not discussed on the Smith chart. I will do it separately because it's gonna be, in fact, yes, I will need to copy that. Copy, and then I will do it separately so you remember it always. Paste, and when I paste it, I will clean it up from all of these things. And in fact, I will do this so it all goes away easily. All right. If I have an impedance, and then from that impedance, I find on the transmission line, obviously, I find the circle for the transmission line. All right. So let's assume I'll get one impedance just randomly. Let's assume that I get this impedance. So that impedance here is Z, and I call it ZA, all right? This is ZA, and it's 1 plus J1. It's random. Now, let's assume that that is a normalized load on a transmission line. So I'm gonna, as I said before, I'm gonna go and find the circle that goes through this point. Make it a little thicker, as a matter of fact. There, so we can see it. All right, do you know how to find the admittance that corresponds to that impedance? Probably not, we have not discussed it. I'll tell you, yes. Yes, yes, it's gonna be the flip side, all right? I mean, the and the diametrically opposite. I think that's how we saw it, all right? So I write here the diameter that goes from this point through the center, okay? From this point through the center. See where that hits. Let me also make it, because these are all, I make them dotted because these are all lines just to help us, all right? They are auxiliary lines. They're not like primary, like a circle. They are just, and then, so this point here is the admittance normalized. When I say normalized admittance, what do I mean? Is divided by the characteristic admittance of the line. So I'm gonna write here that this is the normalized admittance. So practically, what do I mean by normalized impedance? To remind you, normalized impedance means it's like ZA divided by Z naught. Normalized admittance, what does this mean? It's YA divided by Y naught. What is Y naught? Y naught is the inverse of Z naught. Okay? So practically, YA, which is YA over Y naught, is 1 over ZA over Z naught, which is Z naught over ZA over ZA. So the reason I'm saying that is something very important to remember, which is, look at that, YA is equal to 1 over is equal to, let me see, 1 over here, ZA, obviously, all right? And also, you know that YA by A by itself is 1 over, is 1 over ZA. So I'm going here now and I can read it. So if this ZA is what I found there, so I can go now and then find this one, and YA is going to be, if I read it, the real part is gonna be 0.55, and the imaginary part is gonna be minus J, and then I will have to just go here and right at that point is approximately 0.44244. All right, so practically, I find like that, I don't have to go and invert a complex number. If I don't have the capability, or if I am in a hurry and I am experienced on Smith chart, that's how I'm gonna do it. All right, so practically, why am I saying this? If I go here, and now that I have both circles, and I have both loads, why would I go and then try to invert, because I have two impedances in parallel, which means that their admittances will be just the sum. The total admittance is gonna be one admittance plus the other. So why would I go and do anything? I can find it here by doing the following. And I'm going to use now this line so you can see it. I'm gonna drive this line, and therefore I'm gonna go and find, well, I don't need that practically, sorry, because it's the load. That's the load, Z1 from here. So I'm gonna do this line, and then I'm gonna find this point, and that point there is gonna be practically Y input. Let me write it. In fact, I'll do it the same way, so because it's very difficult then to read. So I'm gonna go like that. And this one is y in 1 at bb prime. All right. And also I can do the same thing with this other one. I need to put my arrows, which I didn't here. Because I moved along this line to find the input impedance. It's here. So now I'm going to take this point, also extend it. I will extend it from here, go through the center, and then go and find the diametrically opposite. And that one now, this one, is z, excuse me, y, y2 input at bb prime. And then I can write them here, because I can find how, what is their value. So the first one, the real part of this is by going down here, like that. So it's practically 1.5. And the imaginary part of this, I will move like this to find it along this line. All right, and it's 0.7 plus. And then for the blue, I will move along this line to find the real part. And there, the real part is going to be 2.5, 2.8. And I will, this one is going to be 2.8 plus j plus, you have to move underneath it because you're not going to allow me to write, plus j. And how do I find the reactive part? I move along the circle that gives me the reactive part, which is this one. And the reactive part, this is 0.2 above it, 0.3, 2.0 above it, 3.0 below it. So it's 2.2, 2.4, 2.6. So it's about 2.6. Okay, now why is that important? Because then I can find the total impedance or the total admittance of the two by summing them up. So practically I can go to my problem here. Let me take the 2. And then a copy. So I can go here and what am I gonna do? I will go down below, put here, paste, and increase it. And then from these two, I can find the sum, which is I can do easily. All right, so the sum of the two is gonna be y t at bb prime. Did I call that yt? What did I call this here in the circuit? Yt only. I did not put bb prime. Don't want to change the name. Normalized, obviously. And then I can find it is 0.7, 7 plus 6, 13, 3, it's about J here to be 3.3. And then 5 and 8 is 13. 1, 2, 4. So that is the total, the sum. So YT, because they are two in parallel, all right, so I will take this, and I can write it here. I can write that YT from here is the inverse of ZT, all right? So now, since I have YT, I have ZT. You could go over, and then here is what I would like you to do as the next step, all right? Because now go a new Smith chart if you like. I can find where YT is. My YT point, to see that practically you have come very close to the solution. What did I say? Is 4 point, remind me, is 4 point, did anybody write down? Okay, so it's gonna be 4.3. So the real part is here, all right? And where is the imaginary part? Okay, so that is gonna go somewhere like that. And 3.3 is somewhere here. So it's gonna go like this. So that point here, that's my YT. So practically, how are you gonna, now that I have the total admittance, I can, from the circle of the transmission line goes both from the impedance and through the admittance, all right? So for all impedances, if you write the diagonal, the other point is gonna be always the admittance. So since you know your YT, where it is, and this is, say, what kind of color do you wanna use this time? This one. Let's assume that this is this one, which is, we found it, normalized obviously, right? So your YT, then you can write the circle that goes through that, all right? From there, you can find ZT, the diagonally. The circle is very close to the green one, to the big one, you see? They're not gonna be very different. So you're gonna come down here. So from there, if you write the big circle, I would like you to do it. Write the circle that goes through the YT, the transmission line circle. Find from YT, ZT, and then from there, move by 0.1 to find the input impedance. So you do what you notice, it gets complex, but the reason I wanted to do that is like the same thing over and over again. It's not anything new. So far, we have done the same thing twice for each of the transmission line with the circles. Then we found identically the admittances, the same process. We added the admittances, and now you're gonna do one more. Once more, you're gonna write the circle. You're gonna find from the admittance its impedance, and then from there you're gonna move the same direction also, like we did before, to find the input impedance. So it's always the same thing. That's what I wanted to show you. I took a long time because I went slowly, and that's how long it's gonna take you. But remember, there is nothing complex, theoretically speaking. There is nothing complex, it's all practice. And my advice also, and my advice will be to do exactly the way I do it. Take your time, put everything down, is the same process. There is no way you can mess this up. There is not too many things that we are doing there, all right? But take it your time to do it. You will do it once, twice, 3 times, and you're an expert after that because there is nothing more to it, okay? That's how you're gonna solve. I solved practically a problem very, very similar to your homework, but it's a different data, so you're gonna have to do the same thing for your homework, all right? Any questions?
I just wanted to verify. So when you look for the complex value, you just like look on the circle, like along the outer edges, and then the inner.
No. For the complex value is the inner circle. This one.
Sorry, yeah, that's what I meant. Like when you go.
The outer is when you see where you are and when you are moving. This one. That's what I call outer.
Wait, I didn't mean I didn't.
I got it. Yes, I got it. Just in case, I wanted to clarify. So, just in case.
Okay.
And I'm gonna put this up on this example. I'm gonna put it up by tomorrow. So you're gonna have it available as you solve your homework. All right. Any other questions? Not from point, you will always go from the left. So you'll go around your circle until your circle, you will never go from the right side of the circle. You will go from this point, say from this one, down with a straight line, and then measure it from there. Always from that side of the circle, not the other side. This is what I'm saying. Look at that. Did you see where I put it? Yes, exactly. And then you draw the line down. Yeah. What I meant to say is that always that side, not the other. Yeah.
On the very bottom, it says reflection coefficient.
Yes. P means reflection coefficient for power. So forget about that. It's like magnitude squared. You will always look at the one that says reflection coefficient E or I. Any other questions? Okay, ready to go. Thank you. See you later today or on Friday. Thank you.